Okay, so this one's not quite done yet, though, because a lot of times once you get your numerators condensed, that is still factorable, and that's what's happening here. This is still factorable. So we have on the top x plus 4 and x minus 2. On the bottom, x plus 4, and x minus 1, and then we lose that. So there's our final answer, x minus 2 over x minus 1. Okie doke. Then on 4, which similarly we need a common denominator. Similarly, before we figure out what everything needs, we should factor this into x plus 4, x minus 4. So this one already has an x minus 4. This one has an x minus 4. This one does not, but it's got the reverse flipped order of that. So if I just negate that and negate that, now that is turned into essentially an x minus 4. And my top is like a negative 3 instead. Okay, so I'll just put the negative out in front. Then this one has an x plus 4. These other two need an x plus 4. Can I drop my denominators now on this problem? No, because again, it's simplifying, it's not solving. So when I work out my numerators, I get 2x plus 8 minus a 1, and I distribute a negative 3, and I get negative 3x minus 12 all over x plus 4, x minus 4. Combine like terms, I get a negative x. 7 minus 12 is negative 5 over x plus 4, x minus 4. Angie, does that look good to you? Okay. Complex fraction step. What? You have a question? Okay. Did you get the answers that I sent out? Okay. Complex fraction, I know there's a lot of people still kind of using their own method. But what I want you always to do is look at your mini denominators. So if you had a denominator of an x plus y and a denominator of an x, what would this one need? An x, and what would this one need? Okay, so your least common denominator would be x plus y. That's what you should multiply the top by and the bottom by to clear your fractions. And we picked those because they are the common denominator of these two, which means when we distribute them to a fraction, it will clear the fraction. Because the x plus y will cancel with that x plus y, and it'll leave us with just 1x. And when I distribute to the second fraction, the x denominator will cancel with that x, leaving me with just minus 1 x plus y. And then in my denominator, I have y, x plus y. There's no clearing of a mini fraction in the denominator because the denominator doesn't have a mini fraction. So that just all becomes one thing. Nothing canceled a denominator there because this was over 1. And so it already, I guess, was canceled. So when you simplify up top, you get 1x minus 1x, which cancels, and then minus y over y, x plus y, and then your y's cancel. So you end up with negative 1 over x plus y. Good? Then what? The two inverse questions. I'll just do one of them. Writing inverses is something that we do for all types of functions. It is the hardest for sure for rationals. Because when you switch the x's and the y's, you have a y in the top and in the bottom. And knowing what to do in that situation is where this becomes a trickier case. So if I have a y in the denominator and in the numerator, I have to cross multiply and get it out of there. So when I cross multiply my x, I get 2xy minus 1x. Have to distribute that x. And I get y plus 8. And now again, if you're solving for y, you have to get all your y's together. And it's not as easy to get them all together because they don't combine nicely. Like I can subtract this y term over to the left, and I can get rid of this non-y term. But it's a little bit trickier than what I'm used to because those y's don't cancel or combine nicely. And if you can't combine them, factor them. Take out a GCF of a y on the left. So when I pull out a y, I'm left with 2x minus 1 equals 8 plus x. Oh, and look at the board and put your pencil down. Divided by 2x minus 1 on both sides. Y equals 8 plus x over 2x minus 1. And you're done, with the exception of f of x has to be written as f inverse of x. So there's your answer. Is that good? Okay. The last one, the transformations one, you have, with a parent graph, with transformations, you want to transform your key features. Okay? So, for example, and I'll just give you the parent graph on the side here. You should know that the parent graph has 1, 1, negative 1, negative 1. Those are two key features. And asymptotes, if a graph has them, are key features. So we have 2 points, 2 asymptotes, 4 key features. You want to take all 4 of those and perform the transformations, which the parent graph looks like this. So what happened to it? Well, we subtracted 1 within the function. So by putting the minus 1 there, we shifted it right 1. And then once that was done, this got multiplied by 3. So that's a vertical stretch by 3. And then we subtracted 2 at the very end, so we shifted everything down 2. If you do those 3 things to each of those 4 features, your graph will present itself. So maybe you start with the asymptote. If I take a vertical asymptote and I shift it right 1, that does move it right 1 unit. So now it's at x equals 1. And if you stretch it by 3, picture me taking this pencil and stretching it vertically by 3. A line is already infinite, so then it just is going to get longer, right? Doesn't really change its location. And if I take a vertical line and then shift it down 2, it doesn't really change its location either. So your vertical asymptote, here's my y-axis, your vertical asymptote just got shifted right 1 unit, essentially. The other 2 transformations didn't really affect it. And then your horizontal asymptote got shifted right 1, still the same line. Got stretched vertically by a factor of 3, still the same line because it's on the x-axis already, and that's where you're stretching from. And then it gets shifted down 2, and that will move it down 2. So it used to be on the x-axis, now it's been shifted down 2. So I have a new set of asymptotes here that's just kind of right 1, down 2. The stretches don't affect asymptotes. And then I'm going to do the same thing with my critical points and to see where this is all sort of cornered. So 1, 1 started there. It got shifted right 1 unit, puts it there. It gets stretched vertically by 3. So right now it's 1 unit off the x-axis. Triple that, and it's going to be 3 units off the x-axis. And then shifted down 2, so 1, 2 puts it there. Negative 1 started there. Shift it right 1. Stretch it vertically by 3, so it's already 1 below. That'll make it 3 below. And then shift down 2 more, puts it right there. And rational graphs are kind of nestled in their own little corners. So the corners are created by the asymptotes. So that goes up and comes down there, and this one goes up to the horizontal asymptote and comes down over here. So take however many critical features whatever graph has and move each feature through that transformation. Okay? What I'm going to want to see at the end are where are your new critical points. So I'll be looking for that one and that one, where the 1, 1 transformed to and where the negative 1 transformed to. As far as the asymptote, or the intercepts, because we did the asymptotes, we have x equals 1 and y equals negative 2. Intercepts, our flashcards say, just set x equal to 0 to find the y-intercept. If I set x equal to 0, 0 minus 1 is negative 1. 3 divided by negative 1 is negative 3. Negative 3 minus 2 is negative 5. And so I should have a y-intercept at negative 5, which happens to be where my critical point was anyway. Yes? For an x-intercept, you set y equal to 0. So that would be 0 equals 3 over x minus 1 minus 2. And solve. How do you solve something like that? What'd you say, Haley? Not yet. Eventually that's what I'm going to do. Lucas, add the 2 over, so it's 2 equals 3 over x minus 1, and then cross multiply. You can't cross multiply with a binomial there. So I cross multiply, I get 2x minus 2 equals 3, add 2 to both sides, 2x equals 5, x equals 5 halves, which is 2.5. And we don't really, did we get there? 1, 2, we could kind of clean that up just a little bit and make it cross at 2.5. Yeah. Yeah, that's the line for the asymptote, that's the line for the vertical. Okie doke. All right, so next I'm going to go over your quiz, and then I'm going to hand it back. I pulled some Regents questions, and the Regents questions on word problems for rationals are pretty random. So this first one showed up a couple years ago. I didn't even know how I would teach this. I don't even know how I could come up with more examples like this. This to me is something that, like I said yesterday, you kind of just have to figure out. And it's rational because, yes, there are variables in the denominator, but there's so much more going on than that. So a manufacturing plant produces 2 different size containers of peanuts. One container weighs X ounces and the other weighs Y pounds. So pick up on the difference, ounces and pounds, first of all. If a gift set can hold one of each size container, which expression represents the number of gift sets needed to hold 124 ounces? So my mind spun when I read this. And so when that happens to me, my method is just make up values for X and Y and come up with what the actual answer would be for those concrete numbers and then work from there. So let's just make up that X is 4 ounces and Y is, I don't know, 2 pounds to keep them small. So if a gift set can hold one of each size container, which expression represents the number of gift sets needed to hold 124 ounces? So how many ounces is in one gift set? One gift set holds one of these, so there's 4 ounces, right? And it holds one of these, which is how many ounces? 16 ounces per pound, right? So one gift set is 36 ounces. So I want to know the number of gift sets that would be needed to hold 124 ounces. So 124 ounces, what operation am I going to do here? Division. How many does that give me? What is it? 3.5. So I'm pretty much going to plug in here and see which one gives me 3.5. I do know, see where they're multiplying 16? They're doing that on the, because 124 is in ounces, they need to change the Y pounds to ounces. So the 16Y makes sense because they're doing 16 ounces times the number of pounds. And then the question is, which order did we do it in? We did 124 and divided to see how many times the gift sets would fit in. So the answer is 3. That's the one. If you actually just plugged in those numbers, that would give you 3.5. Hold on. One more. I'm not going to do it. I'm just going to set it up. Jason, will you start handing these back? So this one, they give you the structure. They tell you that time 1 is the time taken by the first person, time 2 is the time taken by the second person, and time with the B is the time it takes for both of them. So Fred and Barney are carpenters. It takes Fred 8 hours. Just let him be person 1. So this is going to be 8. Barney only takes 6 hours, so that will be the time taken by the second person, so that'll be 6. And they're looking for the time it would take both, so they're looking for T of B. So you're essentially just reading and plugging in numbers where they tell you it goes, and you're just going to solve that for T sub B. Right? Get a common denominator all the way across, drop it, solve it. So this one needs a 6 TB, this one needs an 8 TB, and this one needs a 6 and an 8, so a 48. Drop the denominators, solve. I have some more inverses on here. Couple more there. So I would take a look at this as your homework and try some of these word problems that sort of spell things out. The only other one, too, I want you to look at is exercise 3. This is a system of a rational and a linear. Since y equals 2 over x plus 3, plug that in for y. So you're doing 2 times 2 over x plus 3 minus x equals 3, and you're solving that. That's going to be 4 over x plus 3 minus x equals 3. Get a common denominator all the way across, drop the denominator, solve.